And of course, we had already discussed about the group velocity and phase velocity. Uh, so fiber dispersion is something that we're going to discuss today. Yeah. So these are the textbooks which I've already shared with you. You can go through these contents for further details of these. I've already discussed these transmission characteristics, attenuation. I have this part on uh, the measurement of attenuation. We'll come to this later on. So right now, an important parameter in fiber optic communication is dispersion, because as much as attenuation deteriorates a signal in an optical fiber, dispersion causes indirect losses, because of which your data rate with which you can transmit is limited. So because of that, I wanted to discuss, I've already discussed this attenuation windows with you, right? I've also shared these slides on Google Classroom, so you can go through these later on. Now coming to, yeah, dispersion. So this figure shows an outline of how dispersion occurs. Not exactly how, but what is its effect. Okay, so fiber dispersion results in optical pulse broadening and hence digital signal degradation. So if you see here at the input, you have an optical pulse which is narrow, and at the output the pulse is distorted, it becomes broad, and its amplitude also reduces. So we can say the peak power here and here has reduced quite a lot, and hence we can say this fiber dispersion results in optical power loss. But actually the power is not lost. What has happened here is the power, the x-axis here is wavelength. Fine. So here the wavelength spread is very narrow, whereas here, okay, it's not just wavelength, it's also time. Fine. When we look at fiber dispersion, time is the more critical factor here. So with x-axis as time, we can see that the pulse is becoming broad, meaning you have the, what it indicates here is you have the same power, but it is distributed over more amount of time. Okay, so if you are trying to detect the optical pulse based on the power which was transmitted, the peak power, then this peak power would be somewhere over here. So that amount of power is not received at the output. So it's likely that the receiver may assume that it was not a 1 which was transmitted, but it was a 0. So for in binary decision, this is a very likely result. So we have this is what is the effect of dispersion, meaning when dispersion occurs, this is how its effect is seen in an optical pulse. Now coming down, you see there are different dispersion mechanisms. What are these dispersion mechanisms? These say why these things occur or why the pulse broadening happens. Okay. So the first thing is modal or intermodal dispersion. This is this is a common phenomena in optical fibers, wherein the fiber is multimodal, meaning there are multiple modes propagating along the fiber. Another type of dispersion is the chromatic dispersion. This is also known as the material dispersion, and means this is because of this is because of the material properties, and also to some extent this also depends on the dimension of the optical fiber and the structure of the optical fiber. And another type is the polarization mode dispersion. So in polarization mode dispersion, it's likely that the polarization of the optical pulse, here we see an optical pulse. So this optical pulse may have certain polarization, or it may be a mixture of some polarizations. So in polarization mode dispersion, what happens is the optical fiber need not maintain the polarization of the optical pulse. In that case, the optical pulse, which has, let's say, a simplistic, well, let's consider a simplistic case that the input optical pulse has two polarizations. Okay, if we have two polarizations, then the two polarizations would travel with different velocities. And when the two polarizations would travel with different velocities, the two polarizations would reach the output at two different times. So that would result in pulse polarization mode dispersion. And you can say the effective result of even this polarization mode dispersion is similar to this pulse broadening. Now, what other deterring factor is this dispersion? Because what we discussed right now is that dispersion will make us believe that instead of having received a 1, the receiver thinks that I've received a 0. Okay, so this is what is elaborated here also. What was transmitted at the input is 1, 0, and 1. After a certain distance of time, after a certain distance at time t2, which is greater than t1, the pulses are distinguishable. Okay, so what is the receiver now thinks that if you are trying to receive the signal at t2, then the receiver says that it has received a 1, a 0, and a 1. As we go ahead, meaning at a further time refers to larger distance. So as the pulses propagate for even much higher distance, then this also can be decoded as a 101. But if you look at this last level, the bottom part here, all of these can be decoded as zeros. Okay, so in this way, just by loss of power, we can say that means it's not exactly a loss of power, but um, uh, the signal amplitude or power that is getting reduced at specific times, at the time where you want it to be at a peak. Okay, so with fiber length and distance, the time also increases and the dispersion increases. As the dispersion increases, the pulses, you can see another effect here. The pulses are also overlapping. Okay, So this is one factor which this is another factor which gives degradation in optical fiber communication. So modal dispersion, as I've already mentioned to you, this is more common in multimode fibers. So I think there should be a figure which explains this. Yeah, so this shows how multiple modes can propagate in an optical fiber. So this is a multimode fiber wherein the core dia is much larger, and so corresponding to different values of m, you will have different modes which propagate. So here you can identify that the path of these rays, the path length would vary because the number of reflections it takes. Of course, if you consider an optical signal which propagates along the axis of the fiber, that would be the shortest path. Fine. So as the number of total internal reflections increase, the as the number of total internal reflections increase, the path length of these modes increases. So when the path length increases, the time of arrival of the mode is later than the mode which has gone straight without any total internal reflection. I'm talking about this particular ray. Okay, so this would take the shortest time, and this would be taking the longest time among these three modes. So this is about the different path lengths, and this uh, you can say something like, well, let me show you some more graphical representation. So we can consider we have a single pulse, and that single pulse is split into the three modes here. So all the three modes are likely that the power in the three modes may be almost same. Say if this is around 3 milliwatts, this can be 1 milliwatt, this can be 1 milliwatt, and this can be 1 milliwatt. So because of the path difference of uh, these three modes, what we can assume is that uh, the three pulses would arrive at different instants of time. Okay, so when these three pulses are arriving at different instants of time, then the overall net result of these three uh, pulses added together would be something like this. So this is about dispersion in multimode fibers. This shows the normalized guide index. There's another very important factor which we are yet to discuss, and that is the V number. So when I tell you about the V number, we'll come back to these later on. So modal dispersion results in pulse broadening. Well, this is what I mentioned. So m equal to 0. There's a small typo here. this should be the fastest mode and this should be the slowest mode, because the path length experienced by a ray which goes through multiple reflections, the path length is more, so the time taken by the ray to reach the destination is more. So this would be the slowest mode. And m equal to 0 corresponds to the path where it corresponds to the path which is the lowest. And when we say it is the lowest path length, then this will be the fastest mode. Okay. So because of these multiple modes arriving at the destination at different instants of time. So these are all spaced at different instants of time. And when you add all these four modes, then you have a broadened pulse. This is a small numerical example of how one can find out what is the pulse broadening. So you have a zero order mode which corresponds to m equal to 0, which is traveling near the waveguide axis. I mentioned this before, right? So there's another typo I see here. I believe you're able to understand this. This is L corresponds to the length and V corresponds to the velocity at which the optical pulse is propagating. And we had seen in the previous class that the velocity of the velocity of a pulse which is propagating in a fiber with a core refractive index of n1 is c by n1. So if we substitute this v with c by n1, then the time taken by this particular mode is ln1 by c. Now what is shown here is the highest order mode traveling near the critical angle. This needs some time, which is given by another the velocity of mode. But I'm not sure if this might be true for a different type of fiber, which is the gradient index fiber. But for the step index fiber that we have discussed, the velocity is the same, but the length is what is increasing in this case, right? In this case, since the optical pulse is going through multiple total internal reflections, then the length of this uh, propagation, this increases, and that would depend on what is the angle of angle made by the incident beam with the axis, with the waveguide axis. Fine. So this N2 is refractive index of the cladding, and since the optical pulse is not propagating in the cladding but the core, so N2 should not be considered here. Okay. So this is a rough estimate, we can say, of the pulse broadening due to modal dispersion. So how does this modal dispersion restrict fiber bitrate? So if we are transmitting at a bitrate of 10 megabits per second, which is 10 to the power 7 bits in 1 second, then the pulse duration is 1 by 10 to the power 7 seconds, meaning uh, it is 100 nanoseconds, right? It becomes 10 to the power minus 7 if it goes up, right? So 100 into 10 to the power minus 9, that is 100 nanoseconds. That is the duration of the pulse. So when this pulse of 100 nanoseconds, when this is uh, propagating along the fiber, then broadening occurs because of dispersion, and this may also be because of intermodal dispersion. This can be because of also intersymbol interference. Intersymbol interference refers to this previous case. This one. This is what is intersymbol interference, meaning we had a 1, 0, and 1, but at the receiving end we see that this pulse is overlapping with this pulse. So we say that we have intersymbol interference. So this is where we have this interference.
Good morning. Good morning, sir. Good morning.
So modal dispersion limits the bitrate of a fiber optic link uh, to 10 Mbps. This is a common value for multimode fibers. When we think about single mode fibers, we do not have multimode interference because there's only when we think about single mode fibers, we do not have this particular dispersion, as the mode which is propagating along the fiber is a single mode. So in that case, what splitting of the polarizations, which means different polarizations would travel with different velocities, and at the receiving end, those would arrive at different times, and hence you would see it as a broadened pulse. The bitrate distance product is a very important parameter, which is usually very popularly checked in whenever a commercial point of view is needed. Meaning, if I can transmit 10, as the example here, if I can transmit 10 Mbps of data rate over an optical fiber, and I can also transmit 10 Mbps of data rate over a coaxial cable. So what should I consider? Should I consider transmitting 10 Mbps over an optical fiber, or should I consider transmitting 10 Mbps over a coaxial cable? So here the bitrate distance product is very critical, because the next question that comes up is, how far can I transmit this particular uh, data rate over an optical fiber or over a coaxial cable? If I consider 10 Mbps in an optical fiber with a multimode fiber, this would be limited to about maybe 1 or 2 kilometers. If I consider this over a coaxial cable, this also would be limited to about 1 or 2 kilometers. So the optical fiber as such does not have any major advantage. In that case, commercially, what is cheaper, that would be done. So a coaxial cable is cheaper, so a coaxial cable would be laid instead of an optical fiber. But if we consider a single mode fiber, then this same 10 Mbps can be transmitted over distances of even 100 kilometers. In such a scenario, a coaxial cable would not be able to support such a long length. So an optical fiber becomes the go-to product or the preferred product for such a scenario. So the bitrate distance product gives us an idea of what is the actual information carrying capacity of the channel. A coaxial cable or a fiber or a Cat6 cable or a Cat5 cable and so on. So the pulse broadening and the bitrate, the product of these two gives us an idea of what is the order of magnitude estimate of the supported bitrate. The bitrate distance product, that of course can be given by BL, and that should be less than twice C. N core is the refractive index of the core, and we have already discussed what is NA, the numerical aperture of a fiber. So this also gives a estimate of how far at a specific bitrate you can transmit. So you can see that there is an inverse relationship with the numerical aperture. If the aperture is smaller, then the bitrate distance product would be higher. So this is what I have discussed about transmitting 10 Mbps of data rate over 1 kilometers. So its representation would be 10 Mbps kilometer. And this can be suitable for some local area networks, wherein the distance of connections is less than 1 kilometer. Now, the same system can also transmit 100 Mbps data at for a distance of 100 meters. So, if we think about this 100 Mbps for a distance of 100 meters, then the product remains the same. It is 10 Mbps kilometer. Okay. And same is for 1 Gbps along 10 meters or 10 Gbps along 1 meter or 100 Gbps along 10 centimeters. So 1 terabits per second for a distance of just 1 centimeter. So propagation of such a huge data rate for a distance of 1 centimeter may not be very efficient to look at from a communications point of view, but this also has a very important application when we consider that we want to have a network on a chip. I don't know if you have come across this network on chip concept, but it's possible that on a same chip you can have different components which need to communicate at a very high speed. So that is possible with this optical fiber communication. So even if the distance is say around 1 centimeters, it is very difficult to obtain a data rate of 1 Tbps on a chip with the present technology of RF transmission. So 1 Tbps along 1 centimeters with optical methods is a far more easier way of doing it. Now, so when we come to single mode fibers, it eliminates modal dispersion, meaning multi-mode or different modes will not be propagating in the single mode fiber, so there will not be modal dispersion. But pulse broadening does not disappear altogether. Okay, pulse broadening still is present, and that is attributed in one part to the group velocity. We have seen what group velocity is because uh, we do not have the optical pulse which is transmitted does not have a single wavelength, but it has a small spread of wavelengths that gives rise to frequency dependence of the fundamental mode. And this frequency dependence causes chromatic dispersion. And this is what is the line width. The spectral line width refers to the amount of wavelength spread that is present in a optical pulse. So this is what is a spectral line width. I believe you're all familiar with the half power points. So here also it considers the same half power point. If the intensity is 1, so if the intensity is 1, then half power refers to 0.5. So at 0.5, what is the pulse width? That is considered to be the line width. Fine. Now, there are different types of sources which can be used to transmit these optical pulses. You can see that what is mentioned here is a semiconductor laser. Have you heard about a laser? Anyone who's heard about a laser? I can see some of you are on. Anybody who would like to say, have you seen a laser? Not likely that you have seen it in a lab, but as children, you should have played with them, I think. Have you seen pointers? You've seen pointers, right?
Yes, sir.
Yeah. So these pointers are a class of semiconductor lasers which have very low powers. As such, semiconductor lasers can be very harmful to the naked eye. So it has to be a very low power which can be put in the hands of children. So a pointer is a type of semiconductor laser which has a very low power, and you must have seen that pointer can transmit that laser beam over quite a long distance, and the dimension of the spot that you see, that is very small. And you all, I believe, must have seen LED torches, right? Even at the back of your mobile phones, you have LED torches, right?
Yes, sir.
Yeah. So LEDs are another type of source, and if we consider these two sources, an LED spectrum is something like this, and a laser spectrum is something like this. Okay, I believe you are able to understand the difference. If you look at the wavelength spread of a laser and of an LED, then the wavelength spread of laser is much smaller than that of a LED, and hence we get this dispersion we have this change in dispersion because of the difference in line width. Uh, Delta lambda is much higher in case of LEDs, and this delta lambda is much smaller in case of semiconductor lasers. So here you can see what is the nominal or commonly found line widths for different types of laser sources. So here the first line here the first line shows light emitting diodes or LEDs. So the line width can vary from 20 nanometers to 100 nanometers. There are even some light emitting diodes which have a line width even less than 20 nanometers also. So it is variable. It depends on how it is fabricated. And semiconductor laser diodes, what is shown here is 1 nanometer to 5 nanometers, but even this has come somewhat lower by some advanced techniques of semiconductor laser fabrication, which involve distributed feedback and distributed Bragg reflections. So by involving advanced techniques, it's possible to reduce this line width even further. So this helium neon gas laser, this is a very old technology, and it was very widely used. I believe even now this is pretty widely used. Have you, if you go to a mall, you see barcodes, right? You see barcodes on the products, and when you go to a counter to purchase that, they scan it, right? And from the scanner, you see that usually there's a red light which is coming out, right?
Yes, sir.
Yes. So that red light is that comes from a helium neon laser. So that was one of the first uses of these helium neon laser. Of course, I shouldn't say one of the first uses. It was used much earlier for other, we can say, experimental purposes. But commercially, yes, this was a very popular use. Okay. Going ahead, pulse broadening basically is because of propagation delay differences among spectral components. This is what is chromatic dispersion. So you can see here we have the same input pulse, but this input pulse has different spectral components or wavelength components. So these are the all different wavelength components, and all these wavelength components would propagate with different velocities because of the group velocity characteristics in an optical fiber. And hence what you have here is one pulse which arrives last and one pulse which arrives first, and there's another pulse which arrives in between. And when we club these three together, we have a broadened pulse. I hope this is understandable.
Yes, sir.
So this is about the concept of phase velocity, group velocity, and dispersion. Before going any further, I would like to get your feedback on if you have not understood any part of what I was trying to explain today, you can ask me now, and let's sort out these differences if you have not understood anything. Yes?
Sir, I had a doubt. Sir, if the line width of optical source is small, then there will be less dispersion
Yes.
or less pulse widening.
Yes. Less dispersion refers to less pulse broadening.
Okay, sir. Thank you, sir.
Anyone else? Uh, I was discussing about this phase velocity and group velocity in one of the earlier classes also, and I had discussed about what is the meaning of this kz and omega t. Does any one of you remember what is the meaning of z here? Why is it kz and why not k? Yes, Yashraj? Yashraj?
Direction of propagation.
Yes, you remember well. Z here represents the direction of propagation, and k represents the wave vector. Yeah, the wave number or wave vector. And what is the meaning of omega here?
And frequency.
Omega is not just frequency. Yes, Yakshraj?
Sir, angular
Omega,
frequency.
yes, it is angular frequency. Frequency is f and 2 pi f is omega, which is angular frequency. And t here represents the time. So, what is the behavior of an optical signal as it propagates with an angular frequency omega at certain time t in a direction z with a wave vector k. That is what is the significance of this. We have our expert from NBA, and he is requesting to interact with you. So I leave the floor open to him. Sir, please, you can interact.
Hello, students.
Good morning, sir.
Hello.
Good morning, sir.
Am I audible?
Yes, sir, you're audible.
Oh yeah. How? Hello.
Yes, sir, you're audible.
Yeah. Okay. 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 How many of you are first timers to optics now? We all are in which year? Really?
Third year.
Third year?
Yes, sir, they are in the fifth semester now.
Fifth semester. Very good. Very good.
And this is the fifth class that I am teaching them, sir.
Okay. This is a full-fledged course on. Okay. Hello? Can I?
Yes, sir.
Can I ask you questions to them?
Yes, sir. Sure, sir.
Is fiber a transmission line? Any answers to that?
Yes, sir.
Yeah. Is fiber a transmission line?
Yes, sir.
Oh, why do you say that?
So because in fiber also the information is transmitted in the form of light signal.
Very good. Very good. Very good. I appreciate that. Very good. Okay. Now, do you think that fiber is going to be the only medium in future for carrying information? Otherwise, where do you see the applications of optical fibers?
So right now it is mostly used to provide internet services.
Internet services. Okay. Okay. Any other applications of fibers?
So it is used
That
in
is less susceptible to noise.
Yeah.
It is less susceptible to noise and it provides higher bandwidth.
Okay. Okay. Can we call a fiber waveguide? Have you studied electromagnetic already?
Yes, sir.
Okay. Can we call it as a waveguide?
Yes, sir.
What sort of a waveguide it is?
Cylindrical.
Yeah?
Cylindrical.
Cylindrical. No. What is it, a conductor or dielectric or mixed? Very good. Waveguide is the right answer. Waveguide
You can
is
say what is the
also
material.
a
Sir wants to know what is the material of this
material.
fiber.
Yes. Okay. Now, sir it is a dielectric waveguide. Sir has been teaching this, 5 classes have gone, and the explanation given, the dispersion was very, very good. Now, my question is that at the end of the course, what would you like to have learned? Don't tell me equations. Equations are part and parcel of it. Something physical you should have learned. What do you think you would have learned to become a real distinction as a communication engineer?
Sir, we expect to learn the transmission nature, the characteristics of optical fiber, because for transmission, optical fibers are best as of now, and Geo is also laying the fibers because it has a low attenuation and interference, are very low noise interference, and manufacturing techniques for the such fibers, and basically the propagation, how the light waves propagate, what should be the conditions for total internal reflection, and all these things.
Try to learn it with some applications specified. We can definitely learn about attenuation and other things, but that's good. So, do you get to do assignments?
Yes, sir.
You do assignments?
Yes, sir. I mean, it is the
No,
fifth class
in
right
this
now.
subject, other subjects also.
Yes, sir. We definitely do it.
We do assignments. How do you think that we can make the assignments more interesting and purposeful? I'm sure you guys will not copy. How do you think we can make assignments more useful, and what is the subject in which your assignments are very interesting? So
Sir,
far,
assignment would be
name a
they would
subject
be
and tell what was it. Anyone can tell.
Sir, I guess in our first year, there was a technical communication subject. So I think the assignments of that subject were particularly very interesting.
What was the interesting there?
Sir, actually, it involved various kind of skills. Like you had to first of all research on the topic that you have studied, and then you will have to present it, and then there was a team. So it was not dependent on the performance of one person. And the team was made on the criteria of student. Like if there was one person who was not able to communicate so perfectly, so we had to encourage him. So this was basically a complete team environment. So I think that's something that we kind of loved.
Okay, very good. Any other answer? Very good. I appreciate that. Yeah. And one general question. Yesterday, I was interacting with students and laboratories. Now, tell me, how do you think, or what do you expect from a lab, and how do you think that the current practices could be improved so that the learning becomes better? No answer?
Sir, I think the current lab focuses on a set of experiments that are already predefined. So I think it definitely serves the purpose of teaching us with the tools but it is not something that feeds our curiosity at every point of time.
Very good.
I think we would like to have something which also involve us as a part of the what will we be doing in the lab.
That's good. So it has to be open and then allow you to explore.
Yes, sir.
Yes, sir, explore in an ethical fashion, like one should not be breaking the tools.
Correct. Because recently I was going through an article about Stanford's culture, why they have enhanced startups in Bay Area. So there they had mentioned the culture is to give open problems and allow people to fail. Doesn't matter, you can explore. Probably we can try that. Okay. I'm really happy that faculty members are spontaneous and students are aggressive enough. Please try to talk to your teachers and find out how best this could be implemented. At least one